Okay, so this problem is about giving a big O estimate for these algorithms. And the directions specifically talk about the number of operations where an operation is an addition or a multiplication. What they mean, and there's a bunch of other words about not caring about comparisons in the for loop. What they mean is look at these lines where we're doing stuff. This is what we're trying to measure. We're going to use big O to say how many times we run these lines. So let's see. There is a button on my screen that won't go away. Okay, I did it. Let's start with A. And our main question is how many times line 4 runs? And then notice line 4 has 2 additions in it. We'll deal with that at the end. So let's see. When we start the first for loop and set I equal to 1, we come to the inner for loop and we run line 4 m times. We go through that inner loop m times. And then we go back to the outer loop, set I equal to 2, and then go do the inner loop another m times. And we just keep going forever until we get to I equals n. We go to the inner for loop, we run it another m times, and we're finally done. So how many times did we run line 4? Well, n times m times. Wow, that's hard to say. This number of times on the screen. That's how many times we ran line 4. And if we're looking at the additions, we did 2 additions each time we ran line 4. So if you were looking at the additions, you could multiply by 2 like this. But then we take big O of this number, and big O doesn't care about these coefficients. So the answer is that this algorithm for A is big O of n times m. That's how much work we're doing, or the complexity. Okay. For problem B, we do the same thing. So first look at this for loop. We're going to run this line right here n times, because we're just doing the for loop n times. Then we'll go and run this for loop, because these for loops aren't nested like they were before. They're just stacked on top of each other. So we're doing the first one, and then we're doing the second one. And we're running this line down here with the addition m times. So we're doing O of n plus m work. And that's the complexity. We can't simplify anymore because we don't know if n or m is bigger. They're both variables here. So just O of n plus m is our final answer. Okay, last one is C. This one's a little bit weirder because the counter I increments by a multiple of 3. We're no longer doing I plus 1 each time. So this while loop does not run n times. Even though it looks like maybe it should, it doesn't. So we need to figure out how many times this while loop is running. And to do that, I like this chart to start with. I'm going to make a list of the value for I and the number of times we go through the loop for that value. So we run through the loop the first time. We start off with I equals 1. And when we run through the first time, we get down to the last line and we multiply I by 3. Then we run through the loop again. We get down to the last line inside the loop and we multiply I by 3 again. So now we've gone 2 times through the loop. Then we go back up, run through the loop again, multiply by 3, and that's the 3rd time through the loop. And we keep doing this. And so on our xth, that sounds weird to say, I don't know, our x time through the loop, I is going to equal 3 to the x. And now we need to figure out when we stop. And we stop once I gets bigger than n. We keep going until as long as I is less than or equal to n. So we stop when I is bigger than n, which is this 3 to the x. when 3 to the x is bigger than n, and x will give us the number of times through the loop, which is what we care about for complexity for big O. So some simplifying here. Take log base 3 of both sides. If you remember exponent rules, the x gets pulled out front. Log base 3 of 3 equals 1. So we're left with x on the left-hand side greater than log base 3 of n. X is an integer. It's going to be the number of times we run through the loop. So if we want to get the exact x, we take the ceiling of log base 3 to the n, or log base 3 of n, not to the n, this number. Ceiling of that, and that equals x. But we're doing big O here, so nobody cares about ceilings. Big O. Except we actually can go a step farther. You may or may not remember change of base formula, this thing that just showed up in the bottom corner. And we can use this to switch bases of logs. So for example, right now we have log base 3 of n. And if we wanted to put that in log base 2 of n instead, we would have to come over here and the formula would say, fix it like this. We can move between log base 3 and log base 2 by this number right here, which is log base 2 of 3. And this is a number. I have no idea what it equals. I forgot to look it up, but it's some constant value. And big O doesn't care about coefficients. So O of log base 3 is O of log base 2. So this is actually our final answer. In computer science, we use log base 2. Final answer, log base 2 of n. Though actually, since the base doesn't matter, you often will see written places. This is just logarithmic time. The complexity is log n. Okay, so to sum up what happened in this problem, when we have nested for loops, we multiply the complexities. When we have stacked for loops, we add the complexities. And when we have a loop where the counter is incremented by some multiple, it doesn't have to be 3, it could be multiplied by like 100. We are in logarithmic time. So take big O of log n. And now we're done. That's the answer for all of them. Why do I never find the stop recording button? Oh, there it is.